Artificial intelligence, or AI, is revolutionizing the world as we know it. At its core, AI empowers computers and machines to replicate human intelligence. This encompasses a wide array of capabilities, including learning from experiences, adapting to new information, and performing tasks that typically require human intelligence. Imagine a world where machines can understand, interpret, and respond to complex information just like humans do. That's the promise of AI. AI is rapidly changing the way we live, work, and interact with the world around us. From self-driving cars to virtual assistants, AI is already making our lives easier and more efficient. AI is also being used to solve some of the world's most pressing problems, such as diagnosing diseases, developing new energy sources, and combating climate change. The importance of AI lies in its ability to automate tasks, improve decision-making, and drive innovation across various industries. By leveraging the power of AI, we can unlock unprecedented levels of efficiency, productivity, and creativity. As AI continues to evolve, it promises a future filled with possibilities that were once confined to the realm of science fiction. Understanding the fundamentals of AI is crucial for anyone who wants to navigate this rapidly changing technological landscape. The seeds of AI were sown in the mid-20th century, when scientists and mathematicians began exploring the possibility of creating machines that could think like humans. The field of AI was officially born in 1956 at the Dartmouth Workshop, a historic gathering of leading researchers who laid the groundwork for this revolutionary field. Early AI research focused on developing symbolic AI systems, which relied on explicit rules and representations of knowledge. However, these systems struggled to handle the complexity and ambiguity of real-world problems. The 1970s and 80s witnessed a period of disillusionment, known as the AI winter, as progress stalled due to limited computing power and data availability. The late 1990s and early 2000s marked a resurgence of AI, fueled by the exponential growth of computing power, the availability of massive datasets, and the development of new algorithms, particularly in the field of machine learning. This period saw groundbreaking advancements in areas such as natural language processing, computer vision, and robotics. Today, AI is experiencing an unprecedented boom, driven by the convergence of several factors, including cloud computing, big data analytics, and the rise of mobile devices. AI is now being integrated into every aspect of our lives, from the smartphones in our pockets to the cars we drive. Artificial intelligence is broadly categorized into three types: narrow AI, general AI, and superintelligent AI. Each type represents a different level of cognitive ability and complexity. Narrow AI, also known as weak AI, refers to AI systems that are designed to perform specific tasks. These systems excel in their designated domains, but lack the ability to generalize their knowledge to other areas. Examples of narrow AI include spam filters, virtual assistants, and recommendation systems. Most AI applications we encounter today fall under the category of narrow AI. General AI, also known as strong AI, represents a level of AI that possesses human-level intelligence and cognitive abilities. A general AI system would be capable of understanding, learning, and applying knowledge across a wide range of tasks, just like a human being. However, general AI remains largely theoretical at this point, and its realization is still a subject of ongoing research and debate. Superintelligent AI surpasses human intelligence in all aspects. It represents a hypothetical level of AI that possesses cognitive abilities far exceeding those of the brightest human minds. Superintelligent AI is a popular topic in science fiction, but its potential benefits and risks are still a matter of speculation. To navigate AI, familiarize yourself with key terminologies. Algorithm: instructions a computer follows to solve a problem. Algorithms enable machines to learn from data and make predictions. Model: a mathematical representation of a system. Models are created by training algorithms on large datasets. These models make predictions or decisions on new data. Training data: data used to train an AI model. Quality and quantity of training data are crucial for AI accuracy. Neural network: AI model inspired by the human brain. Neural networks consist of interconnected nodes processing information. Machine learning: AI that enables computers to learn from data. Machine learning algorithms identify patterns, improving performance. Deep learning: machine learning using neural networks with multiple layers. Deep learning has led to breakthroughs in image recognition and natural language processing. Section 5. Machine learning versus deep learning. Machine learning and deep learning are closely related concepts, but they have distinct characteristics. Machine learning is a broader term encompassing various algorithms that allow computers to learn from data without being explicitly programmed. These algorithms automatically identify patterns and insights from data, enabling AI systems to improve their performance over time. Machine learning algorithms can be categorized into supervised learning, unsupervised learning, and reinforcement learning. Deep learning, on the other hand, is a specialized subset of machine learning that uses artificial neural networks with multiple layers to extract higher-level features from data. These deep neural networks are capable of learning complex patterns and representations from vast amounts of data, leading to breakthroughs in areas such as image recognition, natural language processing, and speech synthesis. In essence, deep learning can be considered a more advanced and complex form of machine learning. While machine learning algorithms typically require structured data with predefined features, deep learning algorithms can learn from unstructured data such as images, text, and audio. Section 6. Understanding neural networks. Inspired by the intricate network of neurons in the human brain, artificial neural networks form the backbone of many AI systems, particularly in the realm of deep learning. These networks consist of interconnected nodes or neurons organized in layers. Each connection between neurons has a weight associated with it, which determines the strength of the connection. The input layer receives the initial data, which is then processed through hidden layers, where complex calculations and transformations take place. Finally, the output layer produces the network's prediction or decision. During training, the weights of the connections are adjusted to minimize errors between the network's predictions and the actual values. Neural networks excel in tasks that involve pattern recognition, classification, and prediction. They have achieved remarkable success in areas such as image classification, natural language processing, and speech recognition. Section 7. AI algorithms and their applications. AI algorithms are the driving force behind AI systems, enabling machines to learn from data, make predictions, and solve problems. Different types of AI algorithms are used depending on the nature of the task and the available data. In supervised learning, algorithms are trained on labeled data, where each input is associated with a known output. The algorithm learns to map inputs to outputs, allowing it to make predictions on new, unseen data. Examples of supervised learning algorithms include linear regression, logistic regression, and support vector machines. In unsupervised learning, algorithms are trained on unlabeled data. The goal is to discover hidden patterns, relationships, or structures in the data without any prior knowledge. Clustering and dimensionality reduction are common unsupervised learning techniques. In reinforcement learning, an agent learns to interact with an environment and maximize its rewards over time. The agent receives feedback in the form of rewards or penalties for its actions, allowing it to learn optimal strategies. Reinforcement learning has been successfully applied in areas such as game playing and robotics. Section 8. The crucial role of data in AI. Data is the lifeblood of AI. The performance, accuracy, and reliability of AI systems are heavily reliant on the quality, quantity, and diversity of data used for training. AI algorithms learn patterns and relationships from data, so it's essential to feed them with relevant and representative data. High-quality data is accurate, complete, consistent, and relevant to the task at hand. Inaccurate or incomplete data can lead to biased or unreliable AI models. In general, more data leads to better AI models. Large datasets provide more examples for algorithms to learn from, resulting in more accurate and robust models. AI models should be trained on diverse datasets that represent the real-world distribution of data. Training on biased or unrepresentative data can lead to unfair or discriminatory outcomes. Section 9. Debunking common AI myths. Despite the rapid advancements in AI, several misconceptions and myths continue to surround this transformative technology. Let's debunk some of the most common AI myths. While AI will undoubtedly automate certain tasks, it's more likely to augment human capabilities rather than replace humans entirely. AI will create new job opportunities and change the nature of work, but it won't lead to mass unemployment. AI systems are only as good as the data they are trained on. Bias in AI typically stems from biased training data or biased design choices. By ensuring fairness and diversity in data collection and algorithm design, we can mitigate bias in AI systems. While large tech companies have been at the forefront of AI research and development, AI is becoming increasingly accessible to businesses of all sizes. Cloud-based AI platforms and open-source AI tools are making it easier than ever for businesses to leverage the power of AI.